So this begins part 3, part 3 of the 4.2 assignment. We'll get through probably 11 and 13 on this video. We're again still looking for the local extreme and the intervals for which the function is increasing and decreasing. And they don't say we have to do it analytically, but we are going to do it that way. And then we can confirm what we find with the graph. So the first thing I should think about is the domain. And at first glance, it looks like we might have a limited domain because we have a denominator. However, it's x squared, so whatever we plug in for x is going to get squared and become positive. And therefore, there's no way we can turn this into 0. So it looks like our domain is going to be all real numbers. So no endpoints to check. And so now it's time for our critical values. So we'll take the derivative. Have to do the quotient rule. So I get negative 1 times x squared plus 4 minus the top, so it becomes plus x times 2x over the entire thing squared. So then let's clean it up before we analyze. Distribute the negative. And it looks like we get x squared minus 4 on top and x squared plus 4 squared on the bottom. So now we'll set the derivative equal to 0, and hopefully you can easily see that that's only going to happen when x squared minus 4 equals 0, or x equals positive and negative 2. We're also going to let our derivative be undefined, and that's only going to happen when the bottom is 0, and once again that analysis shows us that that's never going to happen. So we have two critical values to check, negative 2 and positive 2. So I'll plug in numbers to my derivative in those regions. So the bottom's always positive. So now we just have to focus on the top. Anything bigger than 2 is going to lead us to a positive number. Anything less than negative 2 squared is going to end up being a positive. And 0 inside gives us a negative on top. So we get positive, negative, positive. So now I know for part A, I have a local minimum at 2 comma f of 2. You can find that because we're decreasing and then we're increasing. We have a local maximum at negative 2 comma you find that, increasing to decreasing. So that leads us to a maximum. Part B, we're increasing from negative infinity to negative 2. And then again from 2 to infinity. We are decreasing negative 2 to 2. And I think you should take a look at a graph of that to confirm those results. Okay, so now 13, same thing. Checking out my domain, cosine we can take of anything, and so there is no endpoints, the domain is all real numbers. So we need to focus simply on my critical values. So I get 3x squared minus 2 minus plus 2 sine of x. So now I want to set this equal to 0. And close inspection here shows me I'm kind of in for it on this one. So let's think about how we might be able to solve this. So I'm looking at this to figure out when I can make it equal to 0. With the sine and then the quadratic, it seems pretty clear that this one is not going to be easily done. And so I'm quickly grabbing my calculator and graphing 3x squared minus 2 minus 2 sine of x. And I'm going to graph it. And I see two values right off the bat. And so let's calculate those. I get a graph, and you should graph it on your calculator, but I get a graph that appears very quadratic, which should make sense. Yeah, because it's a quadratic, so this is kind of doing most of the work. This is a constant. This is not a constant, but 2 sine of x, the biggest that's going to ever be is 1 or negative 1, or in this case 2 or negative 2. So really, this is not going to have a lot of influence on the output. So it makes sense that the graph is quadratic. Okay, so real quick, looks like this first 0 right here. So my critical values, I get x equals negative 0.559, and then also get the other one. I get 1.126. We'll go to 3 decimal places. And those will be my only critical values. So I'll put those on my sign chart. Save a little time here. So those are those values. And I've got my graph in front of me. It looks like this. Remember, this is the graph of the derivative. And so I want to know when my slopes are positive and negative. That's the whole point of the sign chart. And my values between these two, right here, are negative. And my values on the others are positive. So my sign chart is filled out for me. And I'm ready to answer the question. Local max at the 0.559 number. So you can do that. We got to find the y value to go with it. So plug it back into the original. And then we have a local minimum at the other value at the 1.126. And again, plug that value back into the function to get the y value. And that's pretty much the end of that question. We already know the increasing based on the sign chart and decreasing. So I'll let you finish that. All right, we'll go ahead and do number 15. And this is the beginning of a new section. And it says, show the function satisfies the hypothesis of the mean value theorem on the given interval. So what that means is the hypothesis of the mean value theorem. Let's read the mean value theorem real quick. The mean value theorem says that if you're continuous at every point on the closed interval a to b and differentiable at every point on the interior from a to b. So that's the hypothesis. So this problem says show the function satisfies the hypothesis. So I need to show that it's continuous. It is continuous because it is a polynomial, and all polynomials are continuous. So I'm just going to give my quick reason why I'm saying it's continuous, since I didn't do any testing. And then, is it differentiable? And my answer would be yes, it's differentiable, because again, it's a polynomial, and the derivative is 2x plus 2, which is defined for every value between 0 and 1. Alright, so part A, I have not really any work to be shown, at least on this one. It's more of a, did you think about it and do you understand it? Alright, part B then says, show that, find each value of C that satisfies the mean value theorem. So the mean value theorem tells us that, let me write this down first. So if our hypothesis is correct, in other words, if it is closed, continuous, and differentiable, which it is, then the mean value theorem says this must happen. And if you look at this, on the interval from a to b, then f of b minus f of a over b minus a, that's simply the slope. So the mean value theorem says if I have a function from a to b, so they're telling us that if I find the slope from a to b, which is also known as the average rate of change, so find the slope of that line, that somewhere there is guaranteed to be a c value, so maybe like right about here, where the derivative at c, in other words the slope at c, is the same as the average rate of change. So in other words, where is the instantaneous rate of change the same as the average? So this is what the mean value theorem says. So now simply what I need to do is I need to find the average rate of change. So let's do that real quick. So that's going to be f of 1 minus f of 0 over 1 minus 0, which is going to be, plug in 1, I get 1 plus 2 plus 1, so that's 4, minus plug in 0, and I get 1 over 1. So the average rate of change is 3. So from A to B, again this picture is not accurate, but it's telling me I went up 3 and over 1 as an average. So now the question is asking, is there a value c, or find the value c where the derivative evaluated at c is going to also equal 3. So in other words, we want the slopes to be the same. So I already found the derivative. And so now the question is, what value of x will also give me a slope of 3? So I just need to plug in 3 for my slope and solve. So I subtract 2, so that gives me 1 equals 2x. So I get a value of x equals 1/2. Alright, find the value of c that satisfies the equation. So I have done that. So let's just recap for those of you who are not quite sure what just happened. The mean value theorem says that the average rate of change over an interval, that a function has to take on its average rate of change someplace. So in other words, right here, the instantaneous rate of change, the derivative, appears to have the same slope as the average rate of change, or the same value. And so it's just a matter of finding the average rate of change and then figuring out what value of x will make the derivative equal that. And we'll go ahead and stop this video here and pick up with number 18 on the next one.